Gravitational lensing and starlight bending result from the bending of light in regions with differing refractive indices. Dear fellow researchers and friends, my name is Joseph George, and today I would like to discuss gravitational lensing and starlight bending effects. We know that when light from a distant object, such as a galaxy, passes near a massive object like a galaxy cluster, its path is bent. This bending causes the light source to appear distorted, magnified, or multiplied, depending on the alignment and relative distance between the lensing object and the background source. This phenomenon acts as a natural cosmic lens, enabling us to study distant galaxies in the universe. There are three main types of gravitational lensing. Strong lensing, where the lensing effect is so powerful that it produces multiple images of the same distant object. Weak lensing, where the lensing effect is weaker, causing only small distortions in the images of distant objects. Microlensing, where the lensing effect is caused by a single, isolated object like a star, rather than a galaxy or cluster of galaxies. In a previous section, we discussed how ether fills space as a result of the conversion of mass defects into ether, which occurs throughout the universe. Ether is another state of matter, and while each individual unit has mass, we do not currently know how to measure it. Gravity attracts ether particles to every massive body, creating a dense region of ether around it. This region forms a bubble that encloses the body. Every massive body has a surrounding bubble. For example, the Moon, Earth, Sun, and galactic center each have their own bubble. The Moon's bubble is located within Earth's bubble is situated within the Sun's bubble, and the Sun's bubble is positioned within the vast bubble of the galactic center. This means that smaller mass bubbles are encompassed by larger mass bubbles. Since a body and its surrounding bubble move together, there is no ether wind to detect. As a result, experiments like Michelson-Morley's would not work. The density of ether is higher near a massive body and decreases with distance, suggesting the creation of an ether density gradient around the body. This gradient affects a region's refractive property, as high ether density corresponds to a high refractive index and vice versa. Consequently, light travels more slowly in regions of high ether density near massive bodies. This offers a fresh perspective on gravitational lensing, as the bending and refraction of light in regions with differing refractive indices lead to phenomena such as starlight bending and gravitational lensing. This significantly impacts our current understanding of the universe. If a ray of light travels from one edge of a galaxy to another, its speed will change multiple times. This implies that the speed of light is not a universal constant, as currently believed, but instead varies with the local ether density. This completely invalidates Einstein's gravitational curvature of space and time. Based on my studies, gravity is simply an attractive force. In the coming video, we will discuss how gravity and speed impact the flow of time.